Welcome to the lecture on first and second generation peer-to-peer networks. So in this lecture we will discuss two very important networks that unfortunately have acquired a little bit of a bad name primarily because they were used to share unlicensed and in some cases illegal content, but they have helped to a large measure determine the direction of work in this area. And furthermore, most advanced distributed systems today owe their rise to such peer-to-peer technologies. So we'll discuss Napster and Gnutella. So Napster was considered the first generation peer-to-peer network. So what is a peer-to-peer network? Here we have a set of machines. No machine is more privileged than the other in general, and they cooperate among each other to provide a large number of files, in the case of Napster music files, to a worldwide community of users. And a second generation kind of Gnutella is an improvement over Napster. We'll discuss how. So the overview of this, we will discuss the protocol, security and privacy issues with Napster. Then we will provide an overview of Gnutella. So we will discuss the details, and finally we'll do a little bit of comparison of Gnutella and Napster. Alright, so what is the history? So this history is roughly towards the end of the 90s. The MP3 format was discovered. The MP3 is an audio format. So what people those days used to do is that they would record these wonderful 5-minute songs, these 5-minute MP3s. And it was roughly an MB a minute. So 5 minutes was 5 megabytes, which was something just about the internet those days could handle. And the main advantage, by the way, of MP3 was that as compared to the previous format, which were WAV files, MP3's format was somewhat much more compressed without any great loss in quality. So that kind of started a boom of MP3 sharing. And a large part of that sharing was an unintended consequence of a technology like Napster, where a large part of this was illegal. And Sean Fanning, who invented Napster, created a dedicated search engine for MP3 files only. The ability to find, trade MP3 files, chat with other users, and an entire community meant to exchange and distribute MP3 files, audio files, music files to whoever required them. So the provider needed a Napster installed on the computer, and there were a large number of shared directory servers over the net. We will discuss that. But primarily all that was required was a Napster client on a computer. Nothing else was required. The basic protocol now. So what the user used to do, so this is a first generation peer-to-peer network, right, around 1999. So what the user did, or let's put it this way, all that the user had to do was open the Napster utility, log on to the server. The server would update its database with a list of files in the client's shared directory. So every client had to share a directory with the MP3 files that the client owns. So in a certain sense, these files were made available to the community. Then let's say the client wanted a certain file, the client would search and write a query string and search for that kind of file. The server would respond with the IP address of the machine that contains the song. The client would establish a connection with the machine with that IP address and get the song, right? So all that the server would do in this case is that it would act as a broker. So once a client logged in, the server would get a list of songs that the client has. And furthermore, if there is a search query, the server would essentially connect it to one more client. And then a direct connection could be established between them and the files could be transferred. So what was the architecture again? Well, the architecture those days, given that it's a first generation peer-to-peer network, this was a centralized architecture with one central Napster server in the middle with a lot of client machines around it. So it was a quintessential example of a client server architecture where we have one centralized server. The server runs or used to run on these three ports, 7777, 888, right, 48s and 8875. So when universities later on started banning Napster, primarily because songs without legitimate legal licenses were being shared, what they basically did is that they closed down these ports, and to a large extent, at least most Napster clients had a major issue. So the message format between the client and the server was very simple. It was length, type, and data. Where length described the length of the message, it was limited to 2 bytes, 16 bits. The type, error, a login message to login with the password, and login ACK, an acknowledgement message. And also what was the version of the Napster that is being used, and also whether the version of the Napster client needed to be upgraded or not. All of this was included in the type of the message, and the data in this case was the actual data that was being transmitted. Alright, so this is what, in a nutshell, a Napster message actually contained, which was very simple, just the length, type, and data. So if you look at Napster right now, in 2021, when I'm recording this video, Napster would appear to be a very simple protocol. So there were mainly three kinds of nodes: clients, lookup servers, and brokers. So brokers were also called servers. So the client first finds the address of a broker by contacting a lookup server. So a broker is basically the server that does most of the job, but the lookup server is a special kind of a server which just gives the address of the least loaded broker in terms of the amount of work it is doing, right? The least loaded broker to the client. The client will establish a regular TCP/IP connection. So at this point of time, if the reader or the viewer of this video, reader of the paper and viewer of the video, are not sure about some networking concepts such as TCP/IP, proxy servers, and so on, I would request them to kindly look it up. So the client will establish a regular TCP/IP channel with the server. The server can give it the address of a peer. Peer is in this case a special term because the peer is essentially one more client which contains a copy of the data. Data in this case is a song. So Napster peer will have 5 concurrent entities. An entity is essentially a software thread. So it will have a coordination entity. So the job of this piece of software is to connect and communicate with brokers, a listener, which will handle incoming connections from peers, right? So if there is a peer which is trying to connect to it, it will handle incoming connections. Upload, download, and push instances. So we will have ample opportunity to take a look at what these software components are. So these will essentially help in transferring files between peers. So if I were to look at the flowchart of Napster, this is what it would look like. So let's look at the online state. So let me maybe start with the offline state. So after offline, when the user wants to log in, the user will connect to a Napster lookup server. That will find the best broker. Then a connection request will be sent to the best broker. The login information will be exchanged, and if the password matches, the client is online. Subsequently, what it will do is that it will let the broker know that it wishes to share a certain number of files that are there in a shared directory. The metadata will be uploaded, and once all the notifications are done, you can say that the client is ready to share. After that, the client can begin searching. So let's say you want to play a certain song. So you write the keywords of the song. The process of searching again will be initiated and a response will be sent back to the client such that the client can then establish a direct connection with the remote peer and get a copy of the song. So the download instance, how does that work? Well, it starts from the download state. It then sends a download request message to the broker and waits for a reply. There are many reasons for the request being denied. It can be an illegal request, which is the remote host cannot upload a file or the file is not there. If the file can be downloaded, the broker sends the download ACK message to the client, which means the client knows that, look, yes, there is a remote peer that has a copy of the file and the file can be downloaded from the remote peer. The contents of the download ACK message are like this, right, which the broker sends back to the original client. So let us refer to these terms like this. We have the client, then we have the broker whose job is to search, right? And then we have another client, but let's call this client the remote peer. So once a download ACK message is received by the original client, it knows that it needs to establish a connection with the remote peer. So the information that will be sent back to it will be the location of the file that includes the remote host name or the IP address and the TCP port. So let's first start with, if the port is non-zero, then you will enter the remote client download state and there is no problem. A message will be sent and then we can download the file from the remote client. However, there is a problem. So let us consider a university setting and the remote client is kind of behind a proxy server, as it is the case in most universities which have their private networks and behind a firewall and a proxy and so on. So in that case, it is not really possible for any machine outside the organization to initiate a direct connection to a machine inside the organization, right? So this will not make sense. If this will not make sense, then Napster did provide a wonderful mechanism, because primarily this was meant for college students to share files. So it returned the special value of 0 for the port and we entered the client upload state, which I will say. So this was a nice trick. So you can think of this was one of the dirty tricks that gave Napster fame as well as infamy, right? So Napster in that sense is extremely controversial because it allowed college students behind these private networks, behind these closed networks to actually establish connections and exchange data. So a key part of this was that if, let's say, the remote peer is, let's say, within a university that does not allow a direct external connection initiated from outside, then a port of 0 is written and we enter a different state called the remote client upload state. We'll see what it is in the next slide. The remote client upload state, slightly complicated, which, as I said, the remote peer is behind a firewall. It thus cannot export a link for download. So then what happens is, so we have the client here, we have the remote peer here, and we have the broker here, right? So it will seek the broker's help. It will send an alternate download request. So instead what the broker will do, it will ask the remote peer to initiate a connection with the client rather than the client initiating a connection with the remote peer. So the client will wait, and since it knows that the remote peer is behind a wall, right, a network wall, it will ask the remote peer that, look, this is the address of the client, and what you do is that you send a message to the client, and then once there is a connection between both of you, then you can transfer the file to the client. So if somebody really doesn't know what is a NAT, a network address translation, and what it means to actually be in a closed network like a university, I would suggest that you kindly look up this piece of networking. And so this is easily understood for somebody who knows the concept. Otherwise, the greatness of this will not be aptly clear. So if you're not able to understand, kindly look it up What you need to look up is called NAT, right? I'm just writing it down, NAT, Network Address Translation. The key idea of NAT is that if the remote peer is within a secure internal network, it is not possible for the client to contact it. However, if the client is publicly visible, then the remote peer can establish a connection with the client, set up a connection with the client. It can then send the metadata and the contents of the song. Alright? So then the client will anyway get the contents of the song, but it will happen via this mechanism. Of course, simpler is if the remote peer is directly visible, then the client will directly send a request to the remote peer and get the song back. But because in a university setting, the remote peer as such is not accessible, the broker will tell the remote peer that, look, since you are behind, since you kind of have a private IP address which starts with 10, which means you are not externally visible, right? So you need to know what a 10.ip address means. So since you are not externally visible, you initiate a connection with the client and get the transfer done. Alright, so I hope that this sticky notion of remote client upload and remote client download is clear. If not, look at NAT. But assuming you know what the concept is, the concept now basically is that even for users where one was kind of behind a firewall in a private network, there was still a way to do it. So now let's come to the upload instance. So when I'm uploading the file, which means when I'm transmitting the file, I receive the ID, receive the file name. I set up the transfer, so I send all the bytes of the file. The upload is over and the connection is closed, so there is no great rocket science in this. Security and piracy, so this is why Napster ultimately got a bad name. So the first is that it's hard for clients to lie. So they cannot give a fake detail such as an IP address, otherwise who do you transfer it to? So the central site, in this case the central site is the broker, has all the control. It is aware of every single transfer, so later on if let's say there is any legal issue, then you can pretty much catch the central site and then there is trouble. So the problem that happened is that millions of people were freely sharing these copyrighted songs. And furthermore, universities were providing free internet facilities. And these facilities, frankly speaking, were being abused. Alright. So by the early 2000s, most universities actually banned the use of Napster. And pretty heavy penalties were put on students and other people who were using Napster to share files for which they did not have legal licenses. And also this did cause a huge amount of revenue loss for the music industry. So the music industry did run after many people pretty hard. But peer-to-peer file sharing did not stop. So the problem with Napster was the issue of the central server, which is aware of everything. So pretty much you get control of the central server, you find every single transfer, and then people are suddenly legally liable. So Gnutella got rid of the idea of the central server. And also later protocols by Gnutella and so on did not limit the sharing just to music files. They brought in all kinds of files. So by the time Gnutella came, which was roughly like, after 2000, all kinds of files could be shared with a reduced legal liability, but still it didn't make a transfer of a file for which the user didn't have a valid license legal. Nevertheless, it was an improvement from a computer science sense at least. Now let's come to Gnutella. So Gnutella is another distributed network. We are calling it a second generation peer-to-peer network. It did remedy some of the flaws of Napster in the sense that it did not have a central server. So then in this case, a Gnutella host, so what we are calling a client or a peer there, we'll call a host over here. It will join the network first by contacting another Gnutella host. So you're assuming that it knows of some other Gnutella host, it can contact it and join. So what it will do is that once it has joined, So it will send a file search messages to its neighbors, and the neighbors will forward the messages to other neighbors. So in a sense, it will dynamically discover the network. So if you consider a graph like this, first it will send a message to its neighbors, then they will forward to their neighbors, they will forward to their neighbors, and so on. So it will know that in its neighborhood, the names of all the files that are there, and of course every message, you don't want the entire internet to be swarmed with messages, right? So every message had a TTL field, a time to live field, that with every hop the TTL was decremented. So ultimately the messages died out. So if let's say that the TTL was equal to k, then this means that within a radius of k hops, right, in a house server, so all the leaf nodes are at a radius of k hops over here, the message used to go to all of them, and the entire list of files used to come, and this is how a node used to initialize itself. All right, and once the server in this case used to reply, the client established a direct connection with it to download the file, and the server in this case is a remote peer to which a request used to go from the client saying that can I get this file from you, and then the remote peer used to say yes if it had the file. A quick overview. So the overview is like this, that search messages are basically, if this is the client, then search messages are sent everywhere within a radius of k hops, and if anybody has the results are sent back. So again, every Gnutella peer would have 4 of these entities, which would be a connection handler to manage connections with other Gnutella peers, a coordination instance which would coordinate connections with other Gnutella peers, a download and an upload instance, as we have seen. Now come to the details. Initially, the connection handler is in the offline state. It opens a coordination connection with another Gnutella peer and sends a connect message. So this would change the state to online. So let us assume that it somehow knows the ID of a Gnutella peer, or there were some open source, openly visible servers which could at least connect you to Gnutella peers. So mind you, there was no legal liability there, because all that it was doing is that it was connecting you to another Gnutella peer, nothing more than that. It was not coordinating any transfer. So technically speaking, or legally speaking, connecting to Gnutella was not illegal, but transferring a file without licenses was illegal, right? So transferring illegal content was illegal. So that's the reason these lookup servers never participated in any information transfer as such. In the online state, the client might ping other peers to find the size of the Gnutella network. Now when it wished to search for something, it entered the search state. So what can happen is that initially, there is some amount of network discovery, and when you discover the network within k hops, each one of them sends the list of files that it has, or the list of files it thinks others have to it. So you create some sort of a localized database. You first search in that. Otherwise, what you do is that you broadcast a search message, and of course every message had a time to live field, which meant it ultimately died out. And this was sent to a large part of the network. And once it was done, if any peer knew who has it, or if they themselves had it, they would return with the search results. And if the particular machine was not behind a firewall, then the Gnutella protocol would start a connection to transfer the file. Otherwise, what you have seen in the previous case, even with Napster, where we had a remote client upload state, we had something very similar here, because again this was made for college students who unfortunately are known to transfer files illegally without licenses. So Gnutella called a similar mechanism the client push request, where again the remote peer, which in Gnutella terminology we also refer to as a server, even though Gnutella does not have a central server, but I'm just going with the terminology that the Gnutella people use, right? So the remote peer in this case would initiate a transfer in the client push model and send the file. That is if the remote peer is behind some sort of a firewall or it is within some internal network. So now let's come to the coordination instance. The coordination instance can broadly receive 5 types of messages. So the coordination instance is broadly looking at 5 kinds of messages. So the 5 kinds of messages that we are looking at here, the first 2 are pretty much network discovery messages, the ping message and the pong message, ping pong. So in the ping message, it is more like a new client joins and then it sends these ping messages to all over its neighborhood with a time to live field. If this is k, every time that we traverse one hop, the TTL field is decremented and the message is forwarded to remote peers. Then the returning, so when it reaches the end, what comes back is a pong message, right? So when the TTL becomes 0, what comes back to the original client is a pong message, which is sent back in the reverse order of peers to the client, right? So what does it, how does it work? Ping, 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 and again back pong, 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 and pong. So when the pong message comes back, we update the local database with information about all the remote peers. So remote peers can do the same too between themselves, right, along the path of the pong message, and the pong and just keep on forwarding the pong messages towards the original client. So this helps clients within a small neighborhood at least share messages between each other and share information between each other regarding which song is there where. All right. So they maintain a localized database because there is no central server, right? So then let's say that we know that a given song is there at some IP address, right? Then we can establish a connection directly. Now let's assume that even after this network discovery, we want a song which we don't know where it is, right? So what we do is, if it exists locally, you take it. Otherwise, we send a search message, right? So basically, if it exists locally, then of course you return back a search result message. Otherwise, the search message is sent where the TTL field is decremented. So the TTL field is always there to stop flooding in the network, and the message is forwarded to the peers. So what do? If we have one client, we just keep on sending search, 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 and so on. And the moment some information is found out, similar to ping and pong, what comes back is search result, and so on. All right. So the search results come back in the reverse order with the address of the remote peer who has it. Right, so we also refer to the remote peer as a server occasionally in Gnutella, but that's not all that common, even though we have done so once in the past. So here again we have the same idea that if a connection can be established with the remote peer, it is fine. Otherwise, if the remote peer realizes from the request that the original client cannot establish a connection with it, what it does is that it creates a new connection, right? And transmits files through an upload instance, right? So this is similar to the client push is similar to the remote upload that we had in Napster when the remote peer was behind a university's internal firewall. So in that case, what would happen is that the remote peer would establish a connection with the client and supply a copy of the file to it. Resiliency wise, if I were to compare, Napster has a mechanism of finding the best broker, doing some centralized load balancing in the sense that it ensures no broker is overloaded. So this is all the advantages you get from a centralized network where you have more control. And also you have a centralized directory for lookup. It's not really a search based system. But here again there is a massive amount of legal liability. Gnutella has reduced that to a large extent by being fully distributed. So the only job of lookup servers in Gnutella is to actually connect them to a host, and henceforth there is network discovery as well as searches within the neighborhood. It is furthermore resilient to network partitions as well, because assume that a network gets partitioned, the subnetwork here does searches among itself and the subnetwork here does searches among itself. So Gnutella in that sense is extremely flexible in the way that it operates, right? So in terms of traffic, scalability is an issue, because whenever you have a centralized server, it does see lots and lots of requests. The requests kind of swamp it, and because of that, what happens is that becomes a performance bottleneck. Gnutella also scalability is a big concern, albeit in a different manner. So what happens is we send a lot of ping pong search and search result messages, and they are all kind of broadcast within a radius of k starting from the client. And if you have many such messages that are being broadcast, then a local network can be full of such search messages, right? Which was not happening in Napster. We just sent a single message to a centralized server and we got a request. But in Gnutella, this issue will happen, where we'll essentially be flooded by these discovery messages, right? Just to find out who has what. So they have different kinds of issues, right? Napster being less resilient, Gnutella being more resilient. Napster not being scalable because you'll have a lot of requests at the central server, right? Gnutella not being scalable because for discovering who has what, and also for these searches, right? A lot of search messages need to be broadcast throughout the network. So they have their own pluses and minuses. But clearly Gnutella, the legal liability is lower. Hence, we are calling it a peer-to-peer network, because in this case, the Gnutella server, the job of the server is only to locate a peer, right? So if there is a new node that is joining, its only job is to locate a peer. Nobody maintains any usernames or passwords or anything, right? So the centralization is not there. It's truly a distributed system. And in a sense that Gnutella doesn't really say that you transfer illegal stuff. Just in case two peers are doing, they are mutually responsible, nobody else. Alright, in terms of search quality, well, Napster needs to link all of its brokers across network. It needs to maintain a centralized database. This is hard to do, but you will get a better result if you can do it. And of course, there are legal issues. The ping and pong search and search result messages have a limited radius. So this can cause Gnutella to miss a lot of files. Right? So given the fact that we have discuss Napster and Gnutella now, where Napster being, let's call it Gen 1, Gnutella being Gen 2, we have seen the legal liability reduce, but this flooding of messages is clearly the issue with Gnutella, right? And furthermore, if let's say two peers are exchanging some data, they are clearly aware of each other's IP address, and all the nodes along the route are also aware of who is searching for what and who gave what search result. So in a sense, anonymity is not fully guaranteed. So we will now see a few more technologies where we can have free net, which was a precursor to the dark web and Tor networks, where anonymity is pretty much guaranteed. So nobody knows what I'm searching for or what I want, right? These are far more anonymous and secure. Again, they have been used to do wrong things and bad things, but from a computer science knowledge point of view, we should know what it is. And then we will come to BitTorrent. So BitTorrent, of course, has seen lots and lots of commercial applications, in the sense most of our modern big systems such as Amazon, Facebook, Google, etc., the key technology that they use is similar to what BitTorrent uses, and here there is no flooding of messages. It uses a beautiful thing called a distributed hash table. So we will discuss that, but this is pretty much the way that we are going, right? This is pretty much the direction in which we are going. So this is where the current lecture ends.